Alright, in this video we're asked to find the electric field due to a line charge with uniform charge density of 5 coulombs per meter. This is the illustration we have going on. So the first step is to identify a typical element and establish a geometry that introduces variables that are constant and variable. So here I draw it out. We have R, which is the distance from the typical element to the point of interest. We have X, which is a constant distance from the line to the point of interest, the horizontal distance. We have dy, which is our typical element. And then we have the infinitesimal electric field that's produced by the typical element. And in addition, we also have theta, which is also variable as R. So next we want to apply Coulomb's equation to the electric field that is created from the typical element. So this is how we go about doing it. Note that dq is simply the infinitesimal typical element in space times our charge density. Okay, now we have to realize that throughout this whole process, we are only concerned with the horizontal component of the electric field because the vertical components will cancel out due to this illustration right here. So for each point above this line, there will be an identical point below the line, which produces an electric field equal but opposite in terms of the vertical direction, which means that practically every vertical direction will cancel out, while only the horizontal components will be added up within our integral. Because of this, we will take into consideration d cosine theta instead of dE as a whole. So when we write down dE cosine theta, we can manipulate cosine theta to write dExr and plug that back into our previous equation for dE to arrive at this expression right here. Now we want to evaluate the integral and set it up with all the variables we have introduced. So K, the charge density, and X are all constant values, so they don't need to be inside the integral because they're not changing. So we can treat them as constants and pull them out the integral. dy and r, however, are changing, so we have to keep that inside. Now, to make life a little easier, we have to rewrite dy and r in terms of a common variable, which will be theta. And by doing this, we'll use a trigonometric substitution with this triangle right here and with this logic right here. So after we use this trigonometric substitution, we simply plug what we have for dy and r back into our previous equation, and we get this. This leads us to cancel out a lot of terms, and we're left with d theta over secant theta, which is simply cosine d theta. And evaluating that integral leads us to sine theta. So now we have to determine the limits of integration, and it's going to be positive 90 degrees and negative 90 degrees. The reason for this is as dy goes to infinity, this angle will become 90 degrees, and likewise as dy goes to negative infinity, this angle will become 90 degrees. So after we plug in our limits of integration, we arrive at this expression right here, which is the electric field at that point of interest.